We're going to start our last Coriolis problem now. And I just want to, before I get started, comment that normally I obviously do this in a lecture hall, and the pages we're looking at I can see really, really easily with my own eyes here, but just the camera situation, the contrast is kind of poor. So if you want to, before you go any further, you may want to just print out the notes that are up on D2L so you can follow along with me, and we'll go from there. So if not, I'm going to get started right here. So what I have here is called a quick return mechanism. So where might one of these show up? There are various things out in the real world that need a quick return mechanism, but this is often what they look like. Allow me to kind of draw this. So picture we have a crank and a follower, or a coupler rather, sorry, wrong word, and like so. So this is a 4-bar mechanism, and so what this is going to do is here's the input. As this goes around, this piece here, okay, will go like this. So it will rock. All right? So then off of that, what you might have is this rocks. You could have perhaps another piece going like so, and then that would link up to a piece here. Okay, and then we'll put in this piece like so. So here we have a 4-bar mechanism that a motor can drive, and then that drives this thing, and so that makes this thing over here could rock. So we could put this thing over here, but let's say it goes like so. And so as this thing rocks, what happens is then this piece itself goes like this. However, as it's going this in one direction, based on the geometry here, this thing will go one direction really fast. Okay? And depending on your situation, you may have a machine where that's beneficial to you. So that kind of just shows you could have one mechanism then driving another mechanism. Okay. Now, and then they're linked. So clean that up. So I'm doing this problem with a bit of a twist to it. What's the twist? Normally, ground is considered link 1. And so suppose we have another link mechanism over here that's driving this one. So the output of this one drives the input of this one. When people in the real world do mechanism analysis, they tend to make the input of a mechanism link 2. Ground is always link 1. The input tends to be link 2. And then you go from there. So given that scenario, here's the input. So there's a motor or another mechanism that's driving this thing. So we know how long this crank is. So this is a crank that would probably is going to just go back and forth. Here's omega. Here's alpha. I'll note that if this went all the way around, it would slam into this thing, so it won't work. So this would most likely be driven by another mechanism, but at the moment, that other mechanism is driving this thing to omega and alpha, which are given right here, 3 radians per second and 9 radians per second squared, respectively. No big deal. And then this is driving the slot, which will have a quick return feature. Fine as well. We know our geometry. We know relative to this pin where this big pin is in this slot. So we got all our geometry down. And the question for this problem is, here we have C, B. Find out what alpha and omega for this are. What's the twist? Okay. Relative to Coriolis, when we normally do this, we would call link 2 the thing that is touched everywhere. That's this piece. And link 3 is the piece that's touched in one spot. This is backwards. Because here's link 2, as I've called it, and it's touched in one spot, and link 3 is touched everywhere. So that looks kind of backwards. All right. So I'll note we could just make this 2 and that 3 and just do it as normal. But in the past, I put stuff like this on an exam. And what has happened is I will purposely label this 2 and this 3 because it just doesn't matter in the end. But when people see this and they try to fit it and do Coriolis, because this piece is touched in one spot and this is and link 3 is touched everywhere, they just panic and stall and the problem is over. So, and then that becomes a teaching moment. Instead of giving you the teaching moment here, after doing this a couple of times in exams and it doesn't go well, that's part of how exams problems often make their way into my lectures. So that kind of gives you some perspective. So this is, in a sense, a little bit backwards. Does it matter? All right, so here's what you've been seeing in the past. We would look for VB on link 3, and we'd say, well, we're going to do VB on link 2, where that was the thing touched everywhere. And then we do a VB3 relative to B2 relative. This nomenclature tells us sit on B2 and see what B3 does, as opposed to sit on ground and what do you think 3 does relative to 2. There's a little slight difference. All right. Well, suppose we brought this to the other side. VB3 minus VB3 to rel. This would allow us to go from the thing touched everywhere to from the thing touched one place to the thing touched everywhere. All right. Now, I want you to look at this minus thing. I can get rid of that minus sign. Oops. Here's the thing touched everywhere. No, this is the thing touched in one spot. I got myself backwards. Here's the thing touched in one spot, the person walking on the merry-go-round. And then what does the person walking on the merry-go-round see the merry-go-round doing relative to him? Okay, so picture just sitting on their shoulders. And considering yourself not to be moving and the merry-go-round to be moving under your feet, equals VB2. Okay? So the only thing we need to do, and then if we wanted to, we could just renumber them and say, well, then just change the numbers 3 for 2. That would become VB2 plus 3 relative to 2 rel VB3, which is the situation we have now. It's no different. Okay? It's no different. So let's go through this and see where we get. We'll just keep that up for a reference. So we can always bring this term to the other side, and then by switching 3 for 2, the perspective, that changes the sign. Done. All right. So let's start with VB and the acceleration of A and B on 2. So I'm calling this 2 because it's the input. It's what's driving this thing. So I have B on 2 sitting here. What's it doing? Well, I know alpha and omega, so that's just omega cross r. For velocity, we get that. And alpha cross r minus omega squared r. For B on 2, we get that. It's completely normal. This shouldn't bother you at all. All right. Now what we want to do is we want to jump from link 2 to what I'm calling link 3. Oops. So how would we do that? We'll start, what are we seeing on 2? So we've already computed that. And now we would simply say, imagine ourselves sitting on 2, what do we see, or link 2, what do we see B on link 3 doing? Okay, so let's think about that. What's going to happen as this goes, as this rotates around this way relative to the slot, this is going to go higher in the slot. So if you're sitting in the slot, sitting in the slot, what you would see the edge of the slot doing is moving backwards relative to you. Okay? And how's it going to move? It's going to move along the center line here. Let's bring this down. How's this going to move? So if you're sitting here, if we let this rotate a little bit, the pin's going to go up. If you're sitting on the pin and you're looking at where the spot was in the slot you were at on the slot has moved kind of back relative to you. It's going this way. So the B's on the slot are all along here, and they're just going to move along this line. At this instance, that is what you would see. So let's just go. Hard to keep all this viewable, but let's see what we have here. So here's the velocity of B on 2. That's what we computed right above here. And I don't know how fast this is going in the slot, so that's my unknown. And I'm just going to, and since I don't know it, I'll just leave it as an unknown and I'll let the signs work for themselves. But I do know the direction. It's going to be along here. If there's 60 degrees here, this is 30, that's 60. So along this line, at this instant, I would see, if I'm here, I will see this B sliding along that line. So that is V slide 3 relative to 2 cos 60x plus sine 60y. And as we do this problem, if this is just too hard for you, do it again. Call that link 2, call that link 3, and solve it that way. And you'll get the same answers. All right? So here we have that. So we just, now, that's going this way. We need to, because we're going to have multiple unknowns, we need to now go to this B on link 3 from here to there. That's what this is. Omega CB cross R from C to B on link 3. Omega cross R. So omega cross 0.3 cos 60x plus 0.3 sine 60y. So we're attacking it going this way to B and then jumping links. That's the Coriolis effect. And then we're coming at it from this way, going up the other way. So that's what we see here. So if we look at this now, we have this side and that side. We have two equations, one in the x, one in the y. We can solve them. And I'll just bring this up. And here's your answers. And notice what we got. V slide 3 relative to 2 was negative. So it's going down towards here. You can't see this up here, but you can picture it's coming down towards that point. That's what we said it should do. Good. And here's, in doing this, we also solve for this angular velocity right here, 0.867 radians per second. Notice the sign is positive. That says counterclockwise. That's what it should do. So we're good. So time to move for acceleration. Doing that one. I'll just orient this way. So we can keep that in view. And let's start the acceleration. We'll have to move this around a little bit, but actually we'll do it this way. So, I want to look at acceleration of B on link 3. That's right up here. So that'll be B on link 2, and then we have to go through a Coriolis exercise to jump to B on link 3. Kind of imagine link 2 is in the center of the pin, link 3 is on this edge of the slot. Okay, those are viewed as sort of different B's. Okay, so to get acceleration of B in link 2, that's just alpha cross R minus omega squared R. All right, we have that. We've computed that already. Then we have to jump from B on link 2 to B on link 3. That'll be via Coriolis. So we have 2. Now notice this, omega CB. This will be another place where people would just go nuts. This is rotating. That's rotating. which one do you use? Omega CB is always, without fail, there is no exception. It is the link that's touched everywhere if it's rotating. It is rotating. So if it's not rotating, that produces a 0, and that's this whole term wipes out. We had one of those problems earlier. So this is rotating. We computed when we did the velocity work what this omega CB was. That's what goes there. Nothing else. Okay? Now the other one, we're going from link 2 to 3. This just adjusts the terms. Whatever 3 is to whatever 2 is relative. So that says, picture yourself sitting on here. What do you see 3 do? Well, this is the thing we figured out just a little bit ago. Okay? This is minus 0.15, and then we had the orientation was cos 60 x sine 60 y. No problem. Now we have this thing. What's this going to be? Same idea. Picture yourself sitting on here. What do you see B on link 3 doing? Well, it's just moving along a slot, so you know the direction, cos 60x sine 60y. Just leave this as an unknown in terms of magnitude. It'll either be plus or minus. The math will work out for you. All right. That's going from this direction to get to, we go here to get B on link 2, flip over here, B on link 3. Now we have to go from down here, acceleration from C to B on link 3, and that'll just be alpha cross r minus omega squared r for CB. That'll give us 2 equations, 2 unknowns. We're ready to run. So here's this top line. Here is the acceleration we computed for B on 2 already. Here's this Coriolis term where we're using omega CB, the proper one, cross, and then here's the V slide that we got last time, or the previous part. A slide, we'll just leave that as an unknown. And we know the direction, don't know the magnitude. We're going to figure it out. Then on the other side, we have this piece, and alpha CB is unknown. So alpha cross r, that's unknown, but minus omega squared r, that's all known. So we have these 2 unknowns here, which you can see. And so all we need to do now is just a bunch of math. So that's what I have here. I equated the x's. We'll bring this up for you. In a lot of our problems, we can equate either the x or the y and solve for one of the terms directly. This one doesn't work that way. There's 2 equations, 2 unknowns. You got to go through the whole process. And that's what's all here. So I go through that process of 2 equations and 2 unknowns. We solve for A slide is positive, so it's accelerating out. And then here's alpha CD, the other term we wanted, 3.23 radians per second squared. So this is, you follow this. This has all the possible twists and turns that could possibly be thrown at you. If you can do this and understand it, and do it multiple ways, like link 2 to 3 or link 3 to 2 and all that, you have Coriolis. You're ready to go. I can't fool you. So we've given you 2 problems that had little tricks in them. We had the one that had, you'll recall, that had this piece that went up and down. Okay. This was the thing touched everywhere, but it had no rotation, so the omega term disappeared. This one, the only trick in it is the links were mislabeled. This wasn't called 3 and 2. And quite frankly, what you can do, if you want on an exam, if I call this 2 and 3, you could just flip the names, and then at the end of the, and when you give me the answer in the end, flip them back. There's a lot of ways to handle it. Find what works for you, and that's fine with me. We'll talk to you later. This finishes up chapter 16. The next chapter we go into is Newton's law for rigid bodies, which will not only deal with F equals ma, but we will also be getting into torques. So we're going to allow things to be rotating and stuff. So it's going to get a bit more interesting. Catch you soon. Bye now.